Okay, good morning, good morning. Hi, hello everyone. Welcome to section number 9, our next to last section. Um, so here's the QR code for today if you guys want to go ahead and scan it and sign in. Our question of the day is what's your go-to coffee order or boba or tea or what have you? Um, now, so there are a couple things to touch base on. For those of you who I had meetings with this week, it was lovely to see you in meetings and to chat and touch base. If we did not have a meeting, then and you're interested in the meeting, send me an email and I'll regroup and try to find a time. There are a few students who have already emailed me that I have been going since last night and just have not had time to regroup and answer those emails, so they're in my inbox. Um, yeah, mid-semester feedback. So because I spent like an hour and a half going through a lot of the feedback last night and reading everything that people have submitted so far. And I wanted to kind of talk about it here in section now because in section 10 we won't have time because section 10 is going to be pretty packed. So one kind of thing that was very divisive about section is some people are like, I love having time to do problems and start on my own in section. And some people are like, that is a waste of valuable section time, which we are always running short on because I don't even know where to start. Which I think that like both are valid. And then some people are like, we need to do harder questions in section. And some people are like, I really wish we would start off with more basics. So it's really mixed. And so one thing I might try is a lot of the problems for today's section we're going to do kind of as a group, and that's just because of the problems. It's not because of the feedback specifically. But in lecture 10 or section 10, I think one thing I want to try is maybe doing kind of an experimental thing of like asking for a student volunteer to like lead us in problem solving, and like we do it kind of back and forth and we like talk through ideas, and it's not you have to be all right, but then it's a way that we can work on the problem solving together where one, you're not just getting the answer, two, you're having to kind of think about what the steps are, and then three, you're getting kind of corrections as we go. So maybe that's a different thing to try to make it a little bit more engaging for everyone. One unhinged comment that I got from probably 20 people is people want section to be longer. I've never heard that in my life. And to the point where like I know I go over regularly by about 10 minutes and I always feel horrible about it. And I'm like, gosh, this is really disrespectful for their time. I should have planned this better. I should have cut this thing. But also at the same time, I'm like, I know if you give me 7 more minutes, it will be helpful for you. And so I try to like be honest of that and like also make it so that there's the video or something or a resource for you to look at later if you can't stay. But yeah, that's wild feedback. And it's almost like I'm thinking about ideas for future summers of what if there was like 3 sections. One was like an hour-long section that was just problem solving for people who have the basics down. One was kind of a medium section about what we're doing now. And one was like a 2-hour, 15-minute section that was more like slower paced. And then students could pick to go to whichever one they could. I like that pedagogically. I feel like that works and like allows students to kind of choose what is the route that's best for them. No idea if Harvard would let me do that. So we'll see. Also, another common suggestion was like, instead of 3-hour lectures, do 90-minute lectures every day. Yeah, that would be so much better. I think everyone, for the most part, thinks that. Oh, no? Oh, controversial. Yeah, 3-hour lectures are horrible. No one wants to do it. Tim doesn't want to do it. I don't want to do it. The only person who's like 3-hour lectures, good idea, is Harvard as a institution. So, I was gonna say like write your representatives, write your dean of Harvard Summer School. I don't know who that is, but there's also the thing of like some people are like the problem set is so long and so big that don't even have time to like study or like engage with other things in the course, and other people are like we have far too few problems. And so, like, those being such, like, contradictory sides, I'm like, yes, both are true. So for those of you who do not know already, on Monday or Tuesday, if you want extra practice, I'm going to be releasing, like, I think 15 to 20 more synthesis problems for y'all and box problems with, like, an answer key. And those should only be done after the PACS exams. The PACS exams are the #1 resource. PDFs of the blank practice exam are posted. Paper copies are in the back. I would highly recommend you get a paper copy. And actually, if you want to go and grab it while I am talking, that would be great so you don't forget later. But getting a paper copy, even if you're a tablet user, it's great because the exam is done on paper. There were kind of mixed feedback for like quizzes being helpful or not. There's mixed feedback, of course, for like the pace of section. But I think for most students, we're doing kind of right, and it's like we're running out of time because we just can't cover everything from a 3-hour lecture in a 90-minute section. One thing I was shocked by is y'all said I'm approachable. Me, never been described as approachable. Even the response, there was one response that I was like, Colton comes off strong, and was like phrasing it in a way of like, yeah, this can be a lot. But like a comment that I've gotten in the past is like, I went to ask Colton a question and I felt like judged and I felt like they thought I was dumb. And I was like, oh, no. I've done a misstep because like I'm very direct in this class, but it is not because I don't think that any of y'all can like not succeed here. And it's not because I think questions are dumb, but like, I was like, oh, okay, something in my overall gesture, tone, affect is communicating this, so I need to be clearer this summer. And I think this summer I started off being like, hey, I'm kind of blunt. It's not a like judgment thing. And I'm glad to hear that that read as being true. Like I try not to lie to y'all. Also, some of y'all were like very, very kind and like caused some like big feels. And it's really nice when you are like putting a lot of time into something and care a lot about it to hear that that is appreciated and well received. And so thank you for that feedback. There were also some responses that were like quite critical, not particularly of me, but of the course as a whole. And the word of warning that I will give if you have yet to fill out the evaluation is remember that we are reading this closely and paying attention. And like I will say that some of the comments, especially towards Tim, have borderlined on rude. And again, I get being frustrated with the class, and I get wanting to communicate criticism of things that you don't think are working. But yes, also like Tim cares, and I think he does a good job. And it is tough to hear. Like there was one comment that essentially says, "This class should not exist. Nothing about it works." It seems like they actively are trying to like not torture you, but like they're praying for your downfall. And I was like, I don't know what to do with this. Because also there were comments that are like, this is the perfect course. Everything about this works together. And I think the reality is somewhere in between, you know? But just a comment on that. But yeah, thank you for the feedback. I know I bring a lot of chaotic energy into the class, but it feels very good to see that received pretty positively. So, whew. Okay. Yeah, next to last section. Our structure for today, we're going to talk on 3 big things. 1 is radicals, radical chemistry. 2, the electrophilic aromatic substitution reactions from lecture yesterday. And then 3, how to study reactions part 3. In terms of the whole like section length and things, I really want to make sure I touch on each of these, but I also don't want to do like a rush job. And so what I'm probably going to do, if there's something I don't get to, is I'm going to officially end section, give people an opportunity to leave, and then maybe go like 10 more minutes. But I will try to kind of be upfront with that just to give you options. Cool. I think we're ready to jump into it. Answer key for the practice exams is going to be posted Sunday. Are there logistical questions before we transition? Yeah. We have to decide. So I know that there will be some more on Wednesday, probably some more on Tuesday. Yeah, I'm sorry that it's a little bit later, but like we're kind of regrouping. Tim is also going to try to do some extra hours, and so like we hear y'all that y'all need more hours, but also it's like the staffing side of it. And like Harvard has said that this class needs this many people, and this many people are paid for this many hours of help room, which is not enough, which is why we do the whole work together policy. The other thing I'll say for my Monday afternoon help room, way less busy than the morning. Like in the morning, I've heard that there are 20, 30 people at a time. Often in the afternoon, there are fewer than 10. So maybe try coming later if you can. Okay. But with that, so let's talk about radicals. So one thing that's nice is when you have already learned one pattern, to apply it to a new thing that's the same pattern. And when we look at the stability of radicals, we see that it's the exact same stability trend as the stability of carbocations. So like primary is less stable than secondary, is less stable than tertiary, is less stable than resonance stabilized. And honestly, that can kind of intuitively make sense, because a carbocation is you are missing 2 electrons, whereas a radical is you are missing 1 electron. In both cases, you are electron deficient, but it's just about what is stabilizing that electron deficiency. And we can either stabilize it by hyperconjugation and resonance. One key difference between radical stability and carbocation stability is, do you remember how we said that a primary carbocation is just never formed? Like, that's a fact that we said. Primary carbocations do not form, they're so unstable. Primary radicals will form, particularly as intermediates in reactions. And so we will see a primary radical pop up later in a reaction, but heads up. So our general radical reaction that we teach you is the anti-Markovnikov addition of hydrogen and bromine to a alkene. So here we have our less substituted side over here, the far end, and we are adding a bromine to the less substituted side, so it's anti-Markovnikov. The reagents that we use is we use HBr to add our H and Br, but normally if it was just HBr, it's Markovnikov. This is our like carbocation intermediate version. And to do this radical anti-Markovnikov, we use some sort of like unstable bond, typically an oxygen-oxygen bond, and generically you can just write ROOR, and you can actually include R for this one. Like, we don't really care about the identity often. And then you need to either include heat in the delta symbol or HV, which is UV light. And I have just like a little bit more detail of like, here are some common radical initiators of like an OO bond, and here's like why we use these, so you can just read it and get a little bit more info. Like, these structures are not important, but it's just kind of like if you want to think a little bit more deeply about it. But for the mechanism, radical mechanisms typically have like a 3-act structure. The first act is called initiation, where our goal is to generate our reactive radical that's going to react with our molecule of interest. And so these arrows are pretty much going to be the same almost every time you start a radical bromination, to the extent that if we asked you to do initiation as part of the exam, these should be like easy money, just because it will be writing this straight up. So get practice writing it. You take a bond and you split it homolytically. So each side gets 1 electron, or it's heterolytic, where one side gets both of them. And then here you wind up with 2 RO dots. RO dot is going to combine with electrons from this hydrogen and bromine bond. This bond's breaking, where 1 electron goes to the bromine, and then the other electron goes with the hydrogen and creates a bond to this RO dot. So this side altogether is going to form ROH, just general alcohol, and then we get Br dot, which is our main like radical initiator that's going to react with our molecule. So that's initiation, Act 1. Act 2 we call propagation, and it's where the main part of our reaction happens. So you will start off with your alkene, and 1 electron of the bond is going to bond with the 1 electron of our radical species here of the bromine, and then we put a radical on the other carbon. Here, why did we form this radical compared to the other option where we put bromine on the other side? I hear whispers of good things, yes. So this is a secondary radical. This is a primary radical. Secondary is more stable, so this is always the one you form. You would never form the primary radical. And if we want to kind of contrast this with what's happening with normal HBr, the like Markovnikov version, in the first step of this reaction, you're adding the hydrogen and making the carbocation here. But in the first step of this radical reaction, you're adding the bromine and then making the radical. So this radical and the carbocation are in the same place, but the difference here is like, what is the first thing that interacts with the alkene in these 2 different versions? So I think it's good to be doing some compare and contrast to the HBr, which you already saw. Okay, and then once here, the only other thing that we have to add is a hydrogen, and another equivalent of our HBr comes along, and we form a carbon-hydrogen bond, and we get another Br dot. And this Br dot can go on and do even more of these radical reactions, and so we say that we are kind of propagating that signal. Like, we started with a radical, we end with a radical, it's going to keep reacting. And here we have like made our product, the anti-Markovnikov addition. And yet, there's Act 3 of the movie. Like when the movie goes on an extra 20 minutes and we didn't care and it should have just ended a little earlier. So the third act is termination. Termination just means doing radical steps that result in no radical. So you could have two Br dots come together, you get Br2, and that's just going to be a side product, and now no more radical. Or you could get this side product here where your radical intermediate from the mechanism could interact with another Br dot instead of HBr, in which case you would get a dibromine thing. Termination, there are so many ways that you can terminate a reaction, and often we just don't care. So like in my 6 years of working in the class, we've never asked students to draw termination steps. So this is going to be our standard reaction. Like this line reaction you can use in box problems and synthesis, and it's really standard and straightforward. And this general mechanism here is like the quintessential version, the Platonic ideal of a radical mechanism. But the mechanisms for radicals that we give you are going to be harder and weird. So we need to, one, know this basics, and we also need to, two, have tools for how to do those harder reactions. And specifically, radicals like to do these two kind of interesting things. One, they like to open rings, and two, they like to make rings. And so let's talk about some strategies for getting into these more complicated radical reactions, and then we'll do some work together. So, piece of advice number one, number your carbons. Figure out an anchor point, molecule-wise, where you can be like, I feel pretty confident that this is this, and then number all your carbons and map on the strontium-TLN products. That's step one. Step two is you make a make and break list of what are all the bonds I need to make in this reaction, and what are all the bonds I need to break. Step three is really just a reality check, or like a kind of don't be fooled. Watch for hidden hydrogens. So if I drew a reaction like this, it's not really clear that this reaction came from an alkene where we also added hydrogen over here, right? You could have gotten to that alcohol from a reduction of a carbonyl or something. So here, if we do a radical reaction, we add a hydrogen, we often don't write it. And so it can be kind of deceptive of, oh, I'm missing this thing that I need to add. And so watch out for that when you're making your make or break list. Check for hydrogens. And the last thing is, as you do more of these radical mechanisms, you'll see some norms. One norm is that most radical steps involve 3 arrows in one step. And you'll start to get a feel for that as you do it. But let's work on this first practice, which is a little bit simpler side, but not just a verbatim HBr addition. So I'm looking at this, I see HBr, ROR delta. This is my tip-off that we are in radical land. So just from the reagents, I know that this reaction needs to add a hydrogen and a bromine, and that it typically does it anti-Markovnikov. Okay. So, well, we had a ring, now we don't. Trying to map things on here. This is where knowing some basic details about the standard mechanism is helpful. Because what's the first step that we do with our alkene? Yeah, we add the bromine anti-Markovnikov. So, which position, 1 or 2 here, which one is the one that we're adding the bromine at? 2. Well, okay. So if this, I'm going to make it purple star. If that's the one that we think that we're going to bromine in, and that's the first step, then would it be safe to assume probably that this is where our purple star is in the product? Because that's where the bromine is. I think that's a pretty safe assumption. Because again, we might do some weird things, we might open this ring, but like the first step is you add the bromine anti-Markovnikov. So from there, we should be able to number everything else. So you can either start numbering in your product or the starting material. I'm going to do in the starting material, and I'm going to go 1, 2, 3, 4, 5, 6, 7. There are different ways that you could number it. It's not really about like how specifically you number it, it's about being consistent. And so that's probably going to be 1, 2, 3, 4, 5, 6, 7. And I really just did this as like, this seems like a straight chain way of numbering it. I could have done 3, 4, 5, 6, 7, but that just looks ugly. So I don't. Okay, so at this point we've done our numbering. We now are ready to make our make and break list. So what's a bond that we make or break here? Yeah, and because we have numbered our carbons, and this is just a tool for us, I'm gonna say we're making a 1 bromine bond, because it's carbon 1 to the bromine. Other bonds made or broken. So yes and yes. So you were saying making the double bond, you were saying breaking a double bond? So you're breaking the pi 1, 2. And then we have another pi bond in the product, so you're making a pi 2, 3. Okay? What else? Mm-hmm. We know they're on top of a ring, so we need to break 3, 6. Anything else? Well, weren't we supposed to add a bromine and a hydrogen? Which carbon did we add a hydrogen to? Well, let me check 2. Well, 2 had 1 hydrogen. Still has 1 hydrogen. Which carbon? 6. 6 had 1 hydrogen. 6 has 2. Hidden hydrogens. Ooh. Yeah. So we need to make a 6H bond. Okay. Fierce. So we already know what our first step should be because we already said it's the bromine adding. So this, I'm going to do it just for practice, and you want to get to where you can do the initiation steps really quick to be easy points. ROOR, homolytically split, 2 RO dot, RO dot, HBr, arom, arom, boop, ROH, Br dot. I know I did that very quick, and I didn't explain it because it literally is just copying down what's in the other column. If we ask you to show the initiation, yes. But like honestly, this is going to be, well, if you have a radical mechanism, or you will have a radical mechanism either on exam 2 or the final, and like it will be a whole page. So, yeah. If we ask you to do it, that's just easier points on that page. So now we have Br dot and we have our starting molecule. And I know that the reaction starts with adding that bromine. So again, right now, all the steps that we're doing are just recreating the standard mechanism. So, which of our goals have we already accomplished in that first step? In terms of make and break. Mm-hmm. Great. So now, whatever our next step is, it needs to help us accomplish more of our make-break goals. So, for example, like, we could do something on 6 and try to add the hydrogen to 6, but does it look very reactive in the structure? No. What's the carbon that looks reactive in the structure? 2, it has a radical. So let's focus on goals that involve 2. Well, we need to make a pi 2-3 bond, right? So we want somehow to put this electron in as 1 electron towards a pi bond, and we need another source of electrons to make that bond. Well, we get electrons from existing bonds. So where should we get the other electron to make the pi bond? 3-6, because we have to break it. And again, it's using our goals to guide us for the steps of the things that are weird. Like the arrows that we are drawing right here are not the standard mechanism for HBr that we showed in class. But this is what happens, and this is how we use this as a tool to guide us. So we're splitting the 3-6 homolytically. 1 electron goes towards making the double bond, and the other one goes onto 6. So at this point, we've accomplished all of our goals except for add the hydrogen. And then this is going to be the standard step from the reaction of another equivalent of HBr comes along, and it adds the hydrogen to get the product, and then we make a Br dot that will live to propagate another day. So that's the method. And truly this method, I have never done a radical question where I don't number my carbons, make a break list. Like, I think it's, not to be too harsh, I think it's almost foolish to go into a radical question and not do this because of how helpful it is. So, strongly recommend, but also live your truth. Also, radicals come back in Chem 27. So, do y'all know the cofactor like FAD or FADH2? So FAD, the flavin molecules, they do radical chemistry. And so you'll see like how FADH2 is an electron shuttle, you know, for like the Krebs cycle. You get to actually see the mechanism of that in Chem 27, which is really fierce. So this is kind of an easier one, yeah? No, doesn't matter. We only care about main characters. We're here for storylines. We're here for the Bachelor recap show, not The Bachelor. So, let's see a harder one. This is a challenge problem. So challenge problem 7, look at it for a minute and then panic. Yeah, I have a 3-membered ring here and a 5-membered ring, and suddenly I have a 6-membered ring. So, shit has gone down. Okay. After we panic, we find an anchor point, and we start assigning carbons. I feel like this nitrogen in the starting material is a nitrogen in the product, right? We have nitrogen here. So maybe that's an anchor point. But also, how do we even get the tip off that this is a radical question? HV. So HV is UV light, and that is our tip off that we are going to be doing radical things. Also, we don't have ROOR. Do we have any bond between 2 electronegative elements, though? A single bond? Yeah. So we have this ON bond. And that's probably going to be the one that's cleaved. And again, single bonds between 2 electronegative elements are ones that are readily cleaved in like UV conditions. And so this doesn't even have HBr. We're not adding a bromine. This is like a completely new radical mechanism that we've never seen. But once we get into it and use our strategy, you are going to be able to solve it. So we have our nitrogen, and then I'm going to number it in the products just to make it look prettier. So I'm going to number like carbon, maybe I'll do blue star over here, and that's carbon 1, 2, 3, 4, 5. So then I number on the starting materials 1, 2, 3, and then it branches. Does it matter which one I call 4 and 5? No, why? Oh yeah. It's kind of arbitrary 1, but also these are symmetric. So like if I call this 4 and 5, 4 is connected to 5 and 3. If I call this 4 and 5, 4 is still connected to 5 and 3. Like it's the same, so it really doesn't matter. Like extra doesn't matter. Okay. So we've numbered. Make and break. Give me a bond, any bond, made or broken. I'll take all the bonds. What? ON, break. What else? What else? Well, a five what? 5, 3. We want to break. Yeah. 3, 5. Sure. What else? Well, based on our numbering here, 3 and 4 are still connected. So, like, if you had numbered it differently, totally. Yeah. 5N. Good, good, good. A pi 3 oxygen. Good. I think that's it. Okay, so let's start off with our first step, which is going to be the homolytic cleavage and getting our first radicals. So just like we did with ROOR, kind of like ROOR, we're going to do these arrows. So blanc, blanc. Now, I'm going to do something that's lazy. You do not do this on the real exam or the real whatever. You draw the structure. But I know I don't care about the rest of the molecule, and so I'm going to call that just R because I don't want to write it. Don't be better than me. Bless you. You will get to a point in your middle that you realize you've missed something, and then you'll go. So typically the process helps resolve it, but we've accomplished our ON break. So now, what goals are nearby a radical that we could work with? Sure. So, maybe this radical can go in, start to make the double bond, and then we need an electron to join in that pi bond. And to get an electron, we have to break a bond. So which bond should we break? Exactly. And then that means the other electron, the 3-5 bond, would go into 5. So, we have this, and we've accomplished 2 more of our goals. It's also really satisfying that most of these steps do 2 goals at once, and it's like, wow, I'm almost done. Oh. Okay. Oh, wait, and I did cross off the wrong one. So the only thing left is we have to make the 5N bond, and like, this is 5, and this is N, and they both have radicals. Yeah. Ooh, that was a weird arrow. Oh, that's... The thing is, radical arrows can look beautiful. And mine often don't. It is. Because the double fishhook arrow, like this, is giving an argument that says 2 electrons are moving. Where the single fishhook are saying 1. And so if you like put double fishhook arrows for everything on this, we'd have to do like a standard like 3 or 4 point deduction for the whole question. Just because it's so fundamental to what radicals are of 1 electron is moving. So, verse what?
Like what if you just made everything 1 hour?
Then either we would be like, I'll give you the benefit of the doubt, or we'd be like half a point. Yeah. But then here we're done. Like, this is a reaction that looks scary, and it's like, oh my gosh, this is not one that we have been directly taught. We did it in 3 steps, and honestly, it wasn't that painful. And now you're done with a challenge problem. So, this is the process. I highly advocate using this system. I hope this was kind of helpful to kind of see it beat by beat. You will either have a radical mechanism question on exam 2 or the final. In the past 2 years, it's been on exam 2. So you will have a radical mechanism in each of the practice exams. I don't know if it will be exam 2 or the final this year. I have not seen the exam. So it might be that you do all the practice for the radical mechanisms and it's not on this exam. It's not in vain because it will be truly 1 week later. Like all the practice is helpful. Cool. Let's do. So benzene, what's she up to? How does she react? Our first family of reactions that we learned yesterday was the electrophilic aromatic substitution reactions. There's also a nucleophilic aromatic substitution, and there are a bunch of cool reactions that you will never learn. So it's out there, though. If you seek it, you can find those hidden reactions. And honestly, they're fiercer. They can do like weird things. You get to diazonium salts, like, but the purpose of these electrophilic aromatic substitutions is to add some chemical root to a benzene ring, and specifically to substitute out a hydrogen for this new thing. And we call it an electrophilic aromatic substitution because the thing that you were putting on acts as the electrophile in the reaction. Now, one thing is, you guys know that aromatic rings like benzene are really stable. So if it's stable, does it want to do a bunch of reactions? No. So particularly here, it's acting as the nucleophile. It's the benzene ring, like a double bond's going to go and grab something. And in order for it to act as a nucleophile, we need a really fierce electrophile. We need an electrophile that is so reactive that even this bad nucleophile can react with it. And so what we do is we form a lot of these good electrophiles in situ, where we like combine two reactants, and then they form this kind of reactive electrophile intermediate in the beaker. But these reactive electrophiles don't just like sit on a shelf. They are formed like right when you need it, and they only exist for a moment before they are immediately reacted with. So, like, again, the aromatic rings being poor nucleophiles, that's why they don't do the alkene additions that you learned in lecture 8. The general mechanism for all of them, every single one does this. The double bond in the ring goes and attacks an electrophile somehow, one of those good electrophiles. And then, when you've done that, you have broken aromaticity. Like, this is now sp3 hybridized, and so the molecule will want to get back to aromaticity as quickly as possible. And so something in the solution is going to come and deprotonate and reform that double bond. Cool. So let's meet our in situ electrophiles. They're really fierce. They're doing a lot of good work. You have the halogenation ones, you have the deactivating acid ones, and the Friedel-Crafts, kind of to divide them into some families. And to be very honest, I'm going to show you what you need to know, but I'm not going to be spending time in section just like going through beat by beat how to form them and like the mechanism steps, because I think that that's studying that y'all can do on your own, and I want to talk about the harder things related to this. But I made a cute little web. It's way less scary than the alkene web. Like, this is quaint at this point. But here are like the reagents, and then here is the reactive electrophile that's formed as the intermediate. And I think it's good to think about both the reagents and what that electrophile is, just as kind of like a benchmark step. So, again, this is a resource for you to look at. The other one that I'm going to mention is with mechanisms, you need to know kind of two key things. One is, how do we get from our starting reagents to that reactive electrophile? And that's going to be kind of weird and idiosyncratic for all of them. Like, they all go through their own special mechanisms, but there are a couple patterns. Like, the bromine one and the chlorine one are the exact same arrows, right? Like, truly, I just did a copy and paste, drag down, and then change the identity of the molecules. Also, the Friedel-Crafts alkylation down here has a really similar first step of like a chlorine associates with AlCl3, and then you have this Cl AlCl3 good leaving group. And then for Friedel-Crafts alkylation, that leaving group just leaves and you're left with a carbocation. So part of this is the kind of what's in black and red of like forming that good electrophile. And then the arrows in blue are like how the benzene ring is going to attack it. And one thing to note is like I put a lone pair here just because it felt weird to have it start from nowhere. But it's really the benzene double bond here that's attacking. And I just didn't want to write out the benzene each time because I wanted to just generalize this for patterns. And so like this is how the benzene ring is going to interact with the electrophile, and knowing specifically how it's going to happen with all of these different ones. So it's a resource to help you with studying. but I'm going to assume that y'all can do it on your own, okay? So one family I do want to talk about, though, is Friedel-Crafts, just because there are some idiosyncrasies there and it can get a little tricky. So Friedel-Crafts alkylation, just to show the mechanism a little first, and then we're going to do some work with it, is like, say you have some sort of like alkyl group, and it's an alkyl chlorine. The chlorine would associate here, you make this, and then your leaving group there would just leave, kind of SN1 style, and what you would be left with is a carbocation. The benzene ring attacks the carbocation, it's added. So, if we look at these two, trying to put it together, one thing that you're going to want to do each time you try to do your Friedel-Crafts is draw what the carbocation would look like for the Friedel-Crafts alkylation. So again, the process is this becomes a leaving group and then it leaves. So if we were to just draw the carbocation here, it would be this, right? Because again, some stuff happens first, but then the leaving group leaves. What type of carbocation is this? Primary. Do we ever form primary carbocations? So the answer to this first question is no reaction takes place, because you simply just won't have like a carbocation formed. And really quick, not to backtrack too much, but one thing that we didn't even clock over here is in this mechanism, we formed a primary radical and we didn't think twice about it. So primary radicals we can form as intermediates, but primary carbocations we cannot. Then if we try the same process over here with the second one, we are going to think about kind of cutting off this chlorine, and then we are going to get this carbocation. What type of carbocation is it? Secondary. Is it stable? Could it form at least? Yes. Is it going to rearrange? Yeah. So what type of shift is going to happen? A hydride or a methyl? Hydride. So we're next to a tertiary carbon. The shift happens. Not to pump y'all up. You'll sound like a classroom that's learning organic chemistry, that like knows your stuff, and like carbocation rearrangements last week were scary, and now you're like, oh, it's a hydride shift, obviously. So, just saying. Okay, so you would form that carbocation, and like that carbocation is where the benzene ring attacks, right? So if I kind of put this as our big electrophilic carbon, and I'm just trying to draw the product, because this is not a mechanism question, this is just line reaction predicting the product. What I would draw is my little benzene ring, and then the carbon right outside of it is the one that's going to be the one that was attacked, the green one. Well, it needs to have two methyls, and it needs to have an ethyl. So does that process of like doing these disconnections and seeing what potential products of this reaction would be, does that make sense in terms of how we would go about it in making the carbocation? The big things is we just need to make sure the carbocation can form, and we need to know whether or not it rearranges. Yeah, come on. You need to know it. I just didn't ask it here. Yeah. So, the question remains, what if we wanted to make this? Like this looks, if we kind of disconnect it, because the easy way to go backwards is you take that off, and then you would have a chlorine. Like that, if we could do Friedel-Crafts alkylation, that's how we could generate what this should be. But we know, again, that that does not work. So our other option for installing those carbons is we could do Friedel-Crafts acylation. So Friedel-Crafts acylation, I'm going to do a completely different color over here. The way it works is we add the same compound there with the chlorine, except for instead of just being an alkyl chlorine, it's an acid chloride. So it has a carbonyl here. And when we do that, what happens is, the fake mechanism wise, we just attach this whole chunk to the benzene ring. Okay, so let's draw it. We would get 1, 2, 3, 4, 5, and we would have the carbonyl here. So I'm going to move this up a little bit. So this at least gets all the carbons where we want it to be. And then we have a fancy trick that we can do, an extra reaction that Tim introduced that's going to be really helpful for things like synthesis. We can first add NaBH4 with MeOH, and that's going to, just lecture 3, reduce the ketone to an alcohol. And then this is the new weird one. We could add H2 palladium on carbon, and what it's going to do is just fully reduce this carbon and get rid of the OH. Now this only works with OHs that are right next to a benzene ring. No other alcohols. So you could not do this, an H2 palladium on carbon, and make it the OH go away. It's only for this specific circumstance. But that would let us get to this product that we want. So, this is kind of tricky now because we have things that we can add to benzenes that look like they could have been added through alkylation, but if we analyze it, we see that alkylation is impossible. So we need to be able to think back and forth between the alkylation version and the acylation version. And like that's the skill I want us to talk about for a minute. How lost are we right now? Are we ready to talk about that, or are we like,
What's the definition of acylation?
Acylation is when you add the carbons that have a ketone on it. Whereas alkylation is just trying to add the straight up alkyl group. So like here, this was an alkylation. Here, this was an acylation. Yeah. You do. She's versatile. Yeah. Cool. So, what I've done for this exercise is we have a benzene ring with a carbon chain on it. And we need to kind of think backwards as to what the intermediates would be if we tried to add it either via alkylation and a carbocation, or acylation and had a little ketone there. So, the way I would just generate my options, not even thinking really deeply, is if I was trying to look at what the acylation intermediate would be, I would just add a ketone everywhere, like right next to the ring. So already, do we see an option here that this is something that does not exist? Yeah, which one of these ketones could not exist? Yeah.
This ain't Texas.
So the carbons, that carbon would have 5 bonds, so like this is impossible. So you know that you could not form this bottom thing through Friedel-Crafts acylation. But the other ones would be valid. Oh, it's just a fast way of not writing all the double bonds. It kind of is talking about like, hey, really the bonding is like between double and single bonds. It's just kind of a lazy way to write it. And you are allowed to write that unless you're doing a mechanism that involves the double bonds. If you're doing a mechanism involving the double bonds, then you cannot use that abbreviation. Yeah. Okay. And then to think back to the alkylation version of these, what we're going to do is we are going to cut off the carbon chain and put a carbocation there and see if that's stable. So here, we would have that carbocation, we would have this carbocation, and we would have this carbocation. So the top one, is it a carbocation that could be formed? No. So this is primary, just can't be formed. So we know that this is the route that we would have to do to make that product. Okay, the middle one here, is that a carbocation that could be formed? No, it's also primary, it could potentially rearrange. So, primary, can't. We know we would have to do the acylation route. Whereas this bottom one, is that carbocation one that can be formed? Great, would it rearrange? No, so that works. So again, this is just getting at some of the nuance that like if you just see like on a synthesis question there's like a alkyl chain on a benzene ring, it could have been the acylation or the alkylation. You'll need to kind of play this game to determine which.
So the second one, for the population side, when you say it can rearranging would stabilize it, but
It would, but that carbocation just would never form. Mm-hmm. Yeah. Yeah. I totally could not hear you. Sorry. Oh, yeah, like if I wanted to go back one step even further, I would draw this here. But the thing that's going to tell us whether or not that route is possible is the carbocation. So that's why I'm only drawing the carbocation. Oh, yeah, like I could also take this back one further and be like, blah, 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 Cl. Like that would be the reagent that you start with. Mm-hmm. Good. I'm going to try to make this blue. So, we are staying in the same topic, but it's kind of a different like mood, so I am going to play a transition. So let's talk about the hard stuff now. You think you know EAS reactions? You do. You're fine. So, if we just start off with benzene, that's the whole previous page. You're good to go. But if we start off with something else already on benzene, then we're playing a different game, and that game is more complicated. So, first of all, we need some nomenclature. If we are talking about something on a benzene ring, we call the positions right next door to it the ortho position. The position opposite of it is the para position, and the one in the middle of that is the meta position. That is a relative labeling system where it depends on which position you're talking about. So if I want to do, starting in this top position, this is where ortho, meta, para are. If I want to start with this position, ortho, meta, and para are relative to it. So like, what's the relationship between X and Y? Ortho. What about W and Z? Meta. What about X and Z? Meta. What about Y and W? Para. Great. Simple enough. But this now lets us understand something. So, benzene, carboxylic acid, benzoic acid. Sure, right? And you don't need to memorize this, is just FYI. Well, if we have an oxygen-oxygen bond, we call that a peroxy bond. So this is peroxybenzoic acid. Cool, fun. And then, if we put a chlorine at the meta position, we now are metachloro peroxybenzoic acid. And who is that? That's our good friend MCPBA. This is her government name. Metachloroperoxybenzoic acid. Now we can finally understand her. We see her. Isn't it great? Like, also, just as a reminder, what does this reagent do? It takes us from an alkene to... Look who's studying. Yeah, no, it's a really fierce reaction. It's one step with like 4 or 5 arrows. I like it. I like it a lot. But anyway, now you can understand the meta. Cool. So, when you are starting off not with just a blank benzene, when something is on the benzene, you have to ask yourself 2 questions. One has to do with the direction, like do we add ortho, meta, para? Or two, you have to ask about activation. So, does that R group that we've added onto a ring, does it make the benzene more or less reactive is the question. And we think about things in terms of electron donating groups and electron withdrawing groups. That's what these abbreviations are for. So if you are thinking about how benzene reacts in these reactions, is benzene the nucleophile or electrophile? Nucleophile, yeah. So if you donated electrons into the ring, there are more electrons in the ring, would it be a better or worse nucleophile? Do nucleophiles tend to have more electrons or fewer? More. Nucleophiles like to have a high energy donor where we've concentrated electrons in one spot. So when you are donating electrons into the ring, you are making that ring a better nucleophile. So we say electron donating groups make the ring more reactive in EAS reactions. In other words, we say that electron donating groups activate the ring, make it more reactive. Whereas electron withdrawing groups, we are taking electrons out of the ring. So if we're taking electrons out of the ring, then that ring has fewer electrons. It's not going to want to go and act as a nucleophile. It's going to make it less reactive towards EAS. So that's kind of the first question. Second question is like where are the electrophiles adding, ortho, meta, or para, and we call them directing effects. These are controlled by resonance. So to summarize the kind of key details, I've made like 2 key facts here. When we have electron donating groups, they are activating, making it more reactive for EAS reactions, and they direct ortho/para. So again, we talked about the activating, putting electrons into the ring, and then the reason why it directs ortho/para is because of the resonance structures. And this is something that I would actually encourage you to like draw out these resonance structures yourself so you can see it. Just because it's a helpful thing to do and will prepare you for more kind of resonance things associated with benzene. Here, if we donate into the ring, we have a resonance structure that's negative here, and it's at the ortho, meta, or para position relative to the nitrogen. Ortho. And then this is what position? And then ortho again. So we see that there are resonance structures that put negative charges on the ortho and para position. So those are going to be the ones that are more nucleophilic, that want to go and attack an electrophile. So that's why electron donating groups are ortho-para directing. And we also have a type of donation that is not resonance. So if we just have an alkane, what's the way that alkanes are electron donating groups? Ooh, good one. Good one indeed. Hyperconjugation. And remember, that's the same thing that's stabilizing a carbocation, of just leaning the bonds over a little bit. And that's a type of donation. Yeah?
If we were asked to add something to enzyme biosynthesis, could we just take something that could be either ortho, like or para, and just add it wherever we want?
Yeah, we're going to get to that. But yeah, if it could be ortho or para and you're wanting to specifically make one, we're going to say you can do both. But literally, it's like this box that I'm about to talk about. Yeah. So, because you have the choice of ortho or para, you're going to get some of both products in reality. So like, for example, here, if you had a methyl group and you were trying to nitrate it, then 61% of the product would be ortho, 39% is going to be para. And it's just because you have 2 ortho positions to choose from and 1 para. And so literally it's like 2/3, 1/3. So that's fine. But if we have a tert butyl here, do you think it's going to be easy to add at those ortho positions? No. And so this, you would only have like 18% ortho, and you'd have 82% para. Some classes are very intense about this, and like you have to get like over 60% yield and blah, blah, blah. We don't care. If there's the choice and you want to make one of them, we say that you are allowed to do that. I would be cautious if it's the tert butyl, because then you should know better. But for other things, generally you can make the one that you want for our class. So that's key fact 1. Key fact 2, electron withdrawing groups are deactivating. As we talked about, they're taking electrons out of the ring, and they direct meta. So in our resonance structures here, we see that we are literally taking electrons out of the ring. We are robbing her in the night. And here we're left with a carbocation. And that carbocation's at the ortho position, then it's at the para position and ortho position. So it's kind of interesting that the charges for both donating and withdrawing, the charges are all in the ortho-para, but over here it was a negative charge. And negative charge makes something more nucleophilic, where here a positive charge makes something less nucleophilic. So what we get is these 3 carbons, the ortho and para, are not going to be good nucleophiles. And so relatively, the meta position is going to be more partial negative, so it's going to be the better nucleophile. It's not that these actually have a negative charge, it's just they have more electrons on it than the ones that have a partial positive charge. So we also have a way of withdrawing electrons that's not resonance. What's our way of withdrawing electrons that's not resonance? Induction. So this thing, this carbonyl, this ketone, it has induction withdrawing, but also has resonance withdrawing, and resonance is kind of the major one. Here, this NH3 This looks really similar to our donor one, right? What's the kind of key difference between this and this? Like, why is NH3 plus not a good donor? Yeah, we don't have the electrons to donate. We have no lone pair. So it can't donate. It's just inductively withdrawing. And we haven't talked a ton about it, but if you put a positive charge on something, it actually changes the electronegativity value because it's making that atom really desperate for electrons, so it's going to pull even harder. So NH2, while that's a good donor, NH3 plus on a benzene ring is a withdrawing group. And so it withdraws via induction, directs meta. One key thing here, a like triple star fact, is nitro groups and sulfonic acid groups are so electron withdrawing and deactivating that they will shut down the ring from doing Friedel-Crafts. So if you have like a nitro group on here and you try to do Friedel-Crafts, alkylation or acylation, she will quite literally say no. She will say no reaction, not at all, not on my watch. And again, it's just because you're taking so much electrons out of it that you can't be a good enough nucleophile. So I made a gaussified chart for you where here this column is activation or deactivation, and then this is directing effects. And we see that all of the activators here, all of them are orthopara, and we see these deactivating groups are meta, and we have one exception here, and that is the halogens. So the halogens, they are inductively withdrawing, right? But technically, there's a lone pair here. This thing's going to be sp2 hybridized by the neighbor rule, and there is resonance donation. Is this a good resonance structure? No. No. Do you have a positive charge on fluorine, the most electronegative element? No. So which of these do you think is going to be the more significant one? Withdrawing or donating? Withdrawing. And that's kind of crazy because normally we think of resonance as being a stronger effect than induction. But in this case, the resonance is so weak that induction really is the main one. And so overall, it's withdrawing. And so we would describe it as moderately like deactivating, or not moderately, sorry, mildly or weakly deactivating. It's taking electrons out of the ring via induction. But yet, if it's deactivating, we said most of our electron withdrawing groups are meta. It's orthopara. The reason why it's deactivating but still orthopara is because directing effects are controlled by resonance. And so even though this is bad resonance, even though this is less significant than induction, directing effects are primarily controlled by resonance. And so based on the resonance structure, there's a partial negative here. And so it's going to direct orthopara. And you can push it all around the ring. So to the halogens, I do say, fluorine, you're the only exception. Chlorine, you are the only exception. Bromine, you're the only exception. Iodine, you're the only exception. And I'm on my way to getting an A in chemistry. So, yeah, that's the only tricky thing. So donating, orthopara, withdrawing, meta, and then the weird exception is the halogens. So where this becomes a game is a classic type of organic 2 question is a tri-substituted benzene synthesis, where essentially you go from benzene and then you add 3 things to the benzene in a synthesis. And the big thing that you have to do is you have to figure out which order to go. Because bromine, nitro group, and alkyl chain, this, you can just look up the reagents. The hard part's not going to be like just recalling the reagents. The hard part's going to be figuring out those directing effects and figuring out the ring activation. So like here, you know that you can do Br with Br2, FeBr3. Tim used aluminum. On all of our instructional materials, we use FeBr3 with bromine and we use AlCO3 with chlorine. Both are fine. Both don't matter, but just something to keep an eye out for when you're checking your work. NO2, you use HNO3 with H2SO4. And then, we have an alkyl chain. So did we add this through alkylation or acylation? What's our way of checking? Let's draw the carbocation. So if we disconnected there, this is the carbocation. Is this a stable carbocation? No. So that means that we must have done this from acylation. So we know that we are actually trying to get this compound, and then we would reduce it down the ketone. So again, getting the reagents, and here it would be AlCl3 and the chlorine ketone, or the acid chloride there. That's going to be the easy part. The hard part's the order. So what I've done is just like mathematically listed out all the possible orders, and we're going to see which ones work and which ones don't. So let's say we added the bromine first. Where does bromine direct? Does it direct orthopara or meta? She's the only exception. She directs orthopara. So if we then try to add a nitro group, did this nitro group add orthopara? Yeah, so this one is valid. Here, did this ketone add orthopara? Yeah, it added para. So that works. Both those are fine. Okay, what if you try to add your nitro group first? Does she direct orthopara or meta? Meta. And it's because withdrawing groups meta directors. So the meta position is going to be these two. Here, did we add bromine at the meta position? No. And again, the way I got these structures was just, I know I want this orientation. So I said, oh, okay, could I get to this structure where I have the bromine in the correct spot if I started with a nitro group? And we said no, because the nitro group's meta-directing, and so we couldn't get this bromine ortho to the nitro group. Okay, what about here? Could this work in terms of directing effects? Yeah, it is meta. But she said no, absolutely not for acyl Friedel-Crafts. Here, this NO2 group is so deactivating that she shuts down the ring for Friedel-Crafts alkylation or acylation. So we could not do that path because too deactivated. Okay, the bottom one, we have the ketone here. Is that going to be orthopara or meta-directing? Meta, it's a withdrawing group. So it's going to direct there and there. Here, do we add bromine meta? No. Here, do we add the NO2 meta? Yeah, okay. So after the first round, we have like 3 options. And then we check. So now we have 2 things. So we have to check the directing effects of both. So the bromine, it directs orthopara to it. So that's these kind of blue dots. And NO2 directs meta to it, and that's these purple dots. So they line up, which is nice. Do we add to the correct position? Is that one of our dots that we could add to? Yeah, so directing effects work. But she said no. She said, you absolutely cannot do a Friedel-Crafts acylation. So we have ruled this out because too deactivating. Okay, over here, the bromine is going to be directing ortho to it. The ketone is going to be directing meta to it. They agree. And then do we add the NO2 to the right spot? Yeah. So this route here, blum, 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 works. That's going to be a correct answer. Okay, and then we fully ruled out these other positions. So like bum, 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 bum. We only have to check one more. Here, ketone directs meta to it, and so it only has one open. The other one's taken by the NO2. And then the NO2 directs meta to it, so here. Did we add bromine to the right spot? No. So oftentimes when we present a question, there's only going to be 1 or maybe 2 correct routes to do. But the tricky part is you need to get to where you're doing this process of figuring out the order without drawing every possible combination. The way you would do it is you would just start adding a thing that you think would be a first good one to add. So like, let's say you want to add the bromine first. Be like, okay, bromine directs orthopara. Then be like, which do I want to try to add next? Do I want to try to do the acylation or the NO2? Well, I don't want to do the NO2 because it's going to shut it down. And so there's a way that you can do it from start to finish that's a little bit more brainstormy, figure it out as you go, but it's not listing out everything. You will have something like this for sure on either exam 2 or the final, maybe both. It's a really great question. And then one of the theory pages on the exam is going to be directing effects and activation. So you really need to know these trends. The other theory question is likely going to be about like carbocation stability, SN1, SN2, or the other one that comes up a lot, that will definitely come up, I'll just say, is aromaticity. So aromaticity is an easier topic of checking whether or not something's aromatic, and so I decided not to cover it here. I did make a video, and do you know where the QR code should be? It should be right in this white space, and I just forgot to paste the QR code. So when I post the annotated version, I'll re-upload the blank one, and I'll have the QR code. I recorded like a 15-minute video of aromaticity. So let me see. I'm 15 minutes on time. I know this was pretty quick, but I feel good at least that I've given you some tools that you can use to go and study and practice with, and I've hit all the main things for EAS that you'll need for like the weekend and the problem set. There is a like practice of this that we could do, but I think it's going to be more fruitful to talk about how to study reactions part 3. Well, thank you for coming to my TED Talk yet again, part 3 of the trilogy. So, exam 1, the challenge was you're just kind of being thrown into the deep end of here's organic chemistry, here's all these different skills, and also here's what is a reaction. Here is like baby's first synthesis. Exam 2, the challenge is not that. Exam 2 is a lot more in the same lane of reactions, and the challenge is you have like 80 or more reactions, depending on how you like count them. Also, the reason why we don't give like an official list is just because you can count it so many ways. Like, do you count Br2 and Cl2 addition to alkanes as 2 separate reactions? Or do you count them as like different flavors of the same one? And so it's hard to get like a definitive list, but I've heard the feedback that a list would be helpful. So I'll work on that. I'll try to think about that. It will not be ready before your exams. Sorry. The historical outline of exam 2, and this correlates with the practice exam, is 3 pages of box problems, 2 synthesis, 2 mechanism, and 2 pages theory/reactivity. We might ask about like why this step in a mechanism happens, things like that. 1 page of the box problems will be substitution elimination. So this is the structure. But if you really look at it, 5 out of the 9 questions on this exam are focused on line reaction level of reactions. So especially for the mechanism is more heavily tested on the final, just because we have more questions and we tend to just ask more with mechanism, because here this test is very line reaction heavy. You will still need to know the mechanisms and line reactions for everything, but I think you need some extra tools for the line reactions and for studying those. We talked about in part 2 the desert island exercises, the dyes, as ways of getting the reaction basics down, of like, can I write the product and can I get the mechanism? And those are necessary and critical to do before doing these next step studying things. So in terms of a timeline, your goal should be to get through problem set 5 as quickly as possible. Like, don't do a hack job, but also like try to be 95 or 90% done by like noon tomorrow. Which I know that's a lot to say, but like, you want to be spending as much time as you can from now until next Thursday studying for the exam. So after you finish preset 5, you should do the reaction basics. Get those down to where you can write the product and the mechanism pretty quickly, where you've memorized reagents. And that, try to have your reaction basics done by Sunday or Monday. Again, it's a fast timeline. You have to do something that's efficient. I highly recommend trying the desert island ones because it is so targeted. So far, I have not had a single student who has actually tried out the dyes, honestly, for like 30 minutes and not found it helpful, even though it's like uncomfy. I would highly recommend it. So then after that, you're going to pivot into general studying, like practice exams, and then this stuff that we're about to talk about that's going to work on essentially 2 main issues with when you have these many reactions. So one is the tractability issue. Like if you are just trying to study a list of 80 things, 80 reactions listed out, that's going to be hard to manage and it's going to feel really spread out. And so something that you do when you're studying somehow needs to engage with that issue and organize it and compartmentalize these reactions. My favorite way to do that is with using reaction families. So like instead of thinking about 10 reactions for exam 1, I would be like there are 3 families. There's the organometallic family, there's the hydride addition family, and then there's the reversible carbonyl addition families. And if you do that with all the lectures, we have maybe 12-ish families total. And that's something more manageable to think about than like 80 or 90 reactions and all the details and flavors. And the other thing I would recommend doing is getting like a blank sheet of paper and like dividing up into the 12 chunks and be like, what are my families? And you don't need to make a super detailed sheet, but like brainstorm what are the reactions in those families and kind of have it on a page where you can see the rough ideas. Just because having a visual compartmentalized version of all the reactions I think would be really helpful. Do not waste hours making that sheet. It really needs to be a rough guide of like, I toss this in this part of my brain. So I would recommend using reaction families to engage with that issue when it feels too spread out. And the other one is integration. So right now, the lectures feel very distinct. You know, like everything kind of stays in its own lane. You learn about the reactions of a certain functional group each lecture. But on a census problem for exam 2 and the final, you might need to use a lecture 3 reaction followed by a lecture 8 one, then a lecture 5, then a lecture 9. And so thinking between the lectures is not something that y'all are used to yet, especially since the problem sets are so focused on that week's like reactions. So here are 3 strategies to try out. One, and this is one I like, is just do like a chemistry little nature walk. I start out with, let's say, an alcohol, and with no plan in mind, set out in a particular direction. I'm like, okay, what do I want to turn this into? I could turn it into a bromine. I should use PBr3. And then alkyl halide, I could do a substitution elimination. Let's use Naomi. I miss her. How's she doing? We need to catch up. Make an alkene, E2. In alkenes, I can do lots of fun things. So I love MCPBA. Let me make an epoxide. Okay. And then, I like the installing 2 functional groups on one side. Let me add like an ether, because ethers are annoying. So let me do HOETH plus, and then that's going to add acid, more substituted side, OET, and then we would have OH here. Back to an alcohol. Why don't I oxidize her? Like chromium, H2O, OH, OET. Now I can do CAD reactions. I could do a DCC. That would be really fierce. DCC, NH2, bump, 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 bump. And then now I have NH, OET, and then 1, 2, 3, 4 carbons. 1, 2, 3, 4. And do you see how I started real simple and I've made a crazy molecule? On the test, you're just going to see the crazy molecules. And I think doing an exam like this, or doing an exercise like this, where you see how kind of brainstorming and going through reactions you know can lead you to something more complicated, is good for gaining skills that you can do the complicated things. And it also gives you this chance to kind of exercise some creativity and put these reactions into dialogue with each other. So I like it as a way of just kind of free association with the reactions, trying to see what happens. Second strategy. Do y'all have friends? Specifically, do you have friends in the class, or at least acquaintances that you'd be willing to text or message or talk to in passing? I see y'all. I know y'all. I know you have friends. What you should do is get together with that friend and in writing, in a text, in an email, something, say, hi, I commit to writing 2 synthesis questions for you, and you will write 2 for me, and we will send them together on the same day and do a little potluck. I call these friend syntheses. Wow. In those syntheses, don't hold back. Try to trip them up. try to do weird things. Write a hard synthesis. And when you give them the syntheses that you made, you should give them an answer key that has all the intermediates and reagents and structures. That is like a full answer key that they could check their answer. And then you should also give them a blank version that's just the starting material product and the number of steps. It is a really fierce way to practice. One, because synthesis problems are gold. Like, you are not going to be able to find synthesis practice anywhere else outside of this course because every other course has different reactions that they are pulling from. It is gold to make it. And secondly, it's gold because it gets you to put yourself in our head of like being, what's a tricky little thing that we could do? Or like, ooh, that would be a kind of fun thing. Where like you get to try to build something and make a problem. I think it's a really excellent way of learning. I would highly encourage you to do that. I would encourage you to do this more than I would encourage you to wait until Tuesday for the extra synthesis problems to drop. Because some of those were taken from past students' friend syntheses that they sent each other. And they said, I want to send it to Colton because I feel proud of this. I'm like, that is actually really fierce. Can I incorporate it in next year? And they said, absolutely. So here. Yeah.
I want to make sure it's right.
So that's also a good practice. Like, I know that it can feel overwhelming, like redoing a synthesis because that's so hard. And if you are not feeling confident, do a shorter synthesis, step one. And then two, give it to them and be like, I'm not sure that this totally works. And then if they are having to see whether or not it works, that's a really great study tool. Like, it really would help both of you if you wrote a synthesis that doesn't work and then you try your hardest to figure it out and you're like doing all these reactions and like putting all of them into conversation and being like, actually, I know myself, I know organic chemistry, I know this doesn't work. Let me tell you why. Or you can send it to me. I can check. So, last thing in our last little time, reaction webs. So you have already seen a reaction web for alkenes, right? Where I gave you one where it's like all the reactions that an alkene can go into form. Well, you can do that same concept with other functional groups, where you draw a functional group in the middle. And when you do this, I would highly, highly, highly encourage you to label the name of the functional group for each one to be actively thinking about those functional group tags. So what are ways I can make an alcohol? Come on. Reduce the carboxylic acid. And I would use lithium aluminum hydride, H plus 4 cup, 1 and 2. You don't need to worry about stressing to write all these down because there will be an annotated version tonight. What's another way I can make an alcohol? What? Reduction of what? Not acid chloride. We already did the carboxylic acid. Ketone or aldehyde, and specifically for this one, we would want the aldehyde. Or we could do an ester. We could do double addition to ester. Remember her? She was way, 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 way back. So all of them are going to use these same reagents. So this, 1. And again, I write the functional group name, aldehyde. Cool. I have an alcohol. What can I make with it? What? Ether. Sure. So Williamson ether. Step 1, NaH. Step 2, put some alkyl halide. Great. What else? Come on. Yeah, y'all are saying the same things. We can do the leaving group families. So we can turn it into a bromine. We can turn it into a chlorine. We can turn it into a tosyl. TSCl pyridine, Socyl 2 pyridine, and PBr3. And it depends. You will know for sure if you have to account for it or not. But like typically, there might be one stereocenter that we care about. But like, yeah. Cool. Other things I could do with an alcohol. How do I make an alkene from an alcohol? Wait, say one. Oh, like, yeah, it would. And here, primary alcohol, we couldn't use concentrated H2SO4 because the leaving group would have to leave and make a primary carbocation. So, yeah. Great. So if we do chromium with pyridine, we get to the aldehyde. If we do chromium with H2O, we get to a carboxylic acid. And I can think of at least 2 more reactions that we can do with it. Not directly. What if I use this reagent? What would that make? It would. So you would have this OET, OET, acetal. And then this was our carboxylic acid, this is our aldehyde. One other one, and this is the one that no one thinks about just because of how it's written. You could add a carboxylic acid in H+, and you could make an ester where that OET is the OR on the ester. That's really fierce because we just did lectures 3, 5, 7 all together. Okay, you know 3 ways of making alkanes. What are they? E1, E2, and Wittig. Okay, I see you. No, you're good. E1, E2. E1, what functional group do we need to start at? Alcohol. And what do we do? I was going to go for we conk it. Just in terms of reagent. Yeah, it has to be like secondary or tertiary. Great point. Great point. Then if we wanted to do the alkane, let's do like a bromine and then Naomi or something. And then for Wittig, we would cut along here, make one side the carbonyl, one side the ylide. You could do either one. I'm going to do this one and CH2 minus PPH3 plus. So right now, the way that this is confronting you is it's as if this was a quiz. When you are doing this as practice, it can be a looking at my notes, gathering myself, finding these reactions, making up the arrows that I need to fill in, and then it can be a quiz for you. Once you've done that work of finding them all and thinking about it, you can separate that into slow work and fast work. But it's just a really fierce strategy to get you to quickly be able to brainstorm functional groups. And so when you see, like, for example, a secondary amine on like a product of a synthesis, if you only know one way of making it, which is from reducing an amide with lithium aluminum hydride, H+ workup, then you know you can use the number of reactions that you know to actually help you narrow it down and figure out what's going on. So the thing that we are not going to do, that I really like this synthesis, and honestly we're at time, so I might like end it, and then if people want to stay for 10 minutes and do a synthesis, you can. This is a fierce synthesis that looks crazy, just in terms of like, oh, touches the ground, something happened here. Like, we have burst things open, we have nitrogens. But one thing that can help us is like nitrogens. This is a primary amine. We only know 2 reactions in the entire course that make primary amines. And again, in our brainstorming, it could either come from an amide or it can come from a nitrile. So that's where this is going to be really helpful for things like synthesis, and this is going to help us speed as well. So these are the 3 strategies to do after you've got those basics down next Monday through Wednesday as you're doing the practice exams. That's all I have for you, really. Thank you for coming to section. I hope that this was helpful in terms of getting you some tools. If you want to head out, please do. I'm going to take a break for like a minute. And then if people want to stay around, I can do this synthesis. Yeah. So there's a TV show, Arrested Development, that I think is before your time, but there's a character, Lucille Booth, could $12.
We're gonna get there, like.
that.
We're gonna get there. Like, so I'm gonna go store. There's gonna be like one man that is gonna be like the dog.
Okay, is this my synthesis group? Let's jump into it. This is an 11-step synthesis. So we're going to try to do it in like about 10 minutes. And we might just do most of the analysis for it, but I think it would be really helpful to kind of start thinking about together. So what should we do when we start a synthesis? Functional groups, map carbons, all good things. So take a minute, try it on your paper. I want you to try to identify all the functional groups. And then I also want you to think about mapping carbons, but the bigger thing, functional groups, and then maybe do some brainstorming. So, functional groups, pretty straightforward. You have the alkene and start, and then you have the means and the product. And the means and the product, I already kind of said the giveaway there. We only know 2 reactions that make amines. So this either came from 2 amides that we reduced, or it came from 2 nitriles that we reduced. Those are our only options. So that's kind of the first steps. And then I would try to start counting carbons, or like mapping carbons, and I would be perplexed, and I would have some questions. I would say, what happened in here on this day? What is a perplexing thing that has happened in this reaction? Great. So if we look at this, we have 1, 2, 3, 4, 5, 6 carbons. So I'll put 6 carbons here, and then product 1, 2, 3, 4, 5, 6, 7, 8 carbons. So one kind of perplexing thing, maybe I'll just do issues. We have to add 2 carbons, and specifically these are making carbon-carbon bonds. What is another issue? The ring. We somehow opened a ring. Work. So, these issues will tell me some important things. We don't know a ton of ways of making carbon-carbon bonds. Could we brainstorm real quick our ways of making carbon-carbon bonds? We could do a Grignard, or lithium, yeah. What's the one that we learned last section that is definitely going to be something on a test? German or Russian Wittig, yeah. So we could do that, which makes the double bond. Other ways of making carbon-carbon bonds. We would need a carbon nucleophile, right? The other one's subtle. I think there might be one other that I'm not thinking of. The other one I'm thinking of is SN2 with a CN minus. Because that's a carbon nucleophile, right? And it's attacking a carbon alkyl halide. And based on brainstorming and knowing that's one of our strategies, we have options of these products. Which do you think we should lean towards? The CN. Because honestly, that would two birds, one stone. If we added two CNs, that adds two carbons, and that would get to our like nitrile, or sorry, our amines at the end. So, like, I think that this CnSN2 has to happen. And then reduction. Like, that's kind of our main strategy so far. But the other issue is the ring opening. So, what reactions have we talked about that open rings? Radicals, but doing messy radicals in a synthesis, we're not going to do. Like, we're only going to do the basic radicals in a synthesis. Carbocation like to do ring expansions, but fully bursting open a ring, not so much. Hydroboration oxidation, which adds an alcohol, not quite, but you can open the epoxide three-membered ring, but we would have to make that ring to open it. How do we bust open an existing ring? There's one reaction. It's the reaction that I refer to as Lord Split Me Open. Ozonolysis? So if we had open a ring, your first thing that you should think, or if you're chopping two things up, ozonolysis, of if you had like a ring and you added O3, ozonolysis, that's going to open the ring, right? So we don't have that yet, but knowing ozonolysis is one of our main strategies for bursting open a ring, that's maybe an idea to pursue. Yeah.
Why would we immediately just find out if the alkynes in the and also, if we were to use a carbocation, could we expand the ring and then break it later? Like, would that?
Yeah.
Like,
We have so much control now. We have 80 reactions, we have tools. We can do these. Like, we see that the double bond's not in the ring, but do you think we could make the double bond in the ring? To make a double bond in a ring, we need a leaving group on the ring. So let's start to do reactions starting with this alkane, and let's try to get a leaving group placed on a ring. So what's our reaction with an alkene? And Layla, you had a great idea here of like, what if we did a reaction that had a carbocation and that expanded the ring? So if we expanded the ring to somehow making like a 5-membered ring, then whatever's on our dangly bit is 1 away from the ring, whereas right now when we add things, it's like 1 or 2 away. But like, generally throw out a reaction that might add a leaving group where you start with an alkene. So name a good leaving group. Tosyl, chlorine, bromine. Which of those would be easy to make from an alkene? Bromine. Why don't we try like HBr? Now we don't want to do the radical version, the anti-Markovnikov, because that would put the bromine over here, and we want to get it closer to the ring, right? So if we tried HBr, that on first glance you might think would be this. Why is that wrong? Because we have a carbocation. Anytime you do any reaction, even a line reaction with a carbocation, you should draw that carbocation intermediate and see if there's a rearrangement. So the first step, we would add the H, we'd get this carbocation. What rearrangement would occur? We would have this ring opening of an alkyl shift. And this is one that we saw and we did together in section 7. Like, this is one of the first kind of weird ones that we saw, but it can happen. And so that, again, it's helpful to number carbons, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1 still has a methyl group on it, and then 2 has the carbocation. And is that going to be our final carbocation, or can we make a more stable one? More stable one. It's next to this tertiary carbon, so it can do a hydroid shift. And again, normally drawing curved arrows on a synthesis is a big, big, big no-no. But here, we're doing stuff with radicals, and we want to take advantage of this rearrangement. And so, you can draw an intermediate structure. None of this gets points. The only thing that gets points is the correct structure. So, when we do this, we would have this carbocation, and this is what our bromine would add to. So our structure is we have a methyl and a bromine on a 5-membered ring now. Okay. Well, if we're trying to get to ozonolysis, we need a double bond on a ring. We have a bromine, which is a good leaving group, so how could we get into an alkene? Like again, our strategy is we want this into an alkene. So something like this. And then we want ozonolysis, break it open. So what reagent should we use? That Conkit, that's only with alcohols. Yeah, yeah. So what are our 3 ways of making an alkene? And Wittig. We've ruled out E1 because we don't have an alcohol. We've ruled out Wittig because we don't have a ketone or aldehyde. E2, what do we need for E2? Strong base. Pick your favorite strong base, like alkoxide. Mine's Naomi. So now we're here. Now, Lord, split me open. Ozone. And then remember, we have our 2 versions of the second step. So we could do reductive conditions or oxidative conditions. At this point, I don't know which one's going to be better. So let's just try one. Which one do you want to try? Both. All right. 50-50 tiebreaker. Did you say?
Is there really few oxygens together?
Sure. You could do it both ways. One might be more efficient, but right now we don't have enough info. So then this is where our disconnection skills for ozonolysis come in handy. If we put carbonyls on either side of where we had bonds. And this one on the end is technically now an aldehyde. Okay. Well, one thing I might do, just to kind of get this looking like a straight chain, kind of like our product, is I might want to write this looking like this. So if I start to number the carbons, 1, 2, 3, 4, 5, 6. Could that be like 1, 2, 3, 4, 5, 6? Does that seem plausible? So I'm just going to take a step and rewrite it, just to make it look nice. Yeah, this just means like, you know, like your 10th grade geometry proofs of congruence. It just says these 2 are the same structure. Side, angle, angle. Oh. Like we would say triangle ABC is congruent to, and they might do like a little wiggle on it too. Triangle DEF. Anyway, so we are trying to get from here to here. And so maybe at this point I will like put this up. And we know that once we get to this structure, we're almost done. Maybe let's try the working backwards thing. How could we get from a nitrile to an amine? What reagent do we need to use? Lithium hydride, I'm hearing a little. So we need to add like a bunch of hydrogens to things. And our main way of adding hydrogens to the nucleophile is lithium hydride. So you would have step 1, LiAlH4, Et2O, and step 2, H+ workup. Okay, so we're really close. All that we need to do is go from carbonyls to cyanides. And with this, we said that we were going to try SN2. So can we somehow turn these carbonyls into SN2 like electrophiles? So like essentially we want to get some structure that we can add NaCN and it's going to do an SN2. So maybe it's easier to like work backwards. What's a good leaving group that you like? OTS, sure. So this could have replaced OTS, OTS. And here it's secondary, so it would be a little bit slow, but it could happen. And now we are having to think, okay, how do we get from aldehyde ketone to OTS? Well, OTS we form from what functional group? from alcohols. Have I lost people, or are we just moving quickly? Moving quickly but not lost. Okay, work. So, we could do the alcohols that came before here. And then we used also chlorine, pyridine. And now, do we know a reaction that's going to go from a ketone aldehyde into alcohols? We do a reduction. And so this, we could even just use the one-step soft boy, NaBH4 MEOH. We've done our synthesis. Steps, we were 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. 1, 2, 3, 4, 5, 6, 7, 8, 10. There we are. Like we had 6 to start with, and then the 2 new carbons came from the 2 CNs, this and this. No, this works. Yeah, I don't know why it says 11 or fewer. Oh, I think that like, if you wanted to do the route that went from this to then the bromines version leaving group and then did the SN2, yeah, like it's just a 2-step way of making the like good leaving group versus a 1-step way. No, that wouldn't be different. Yeah, exactly. Like that could add a 2nd step here, whereas if we use sodium borohydride, it's just 1. So, again, this is a hard synthesis, but our tools of analysis helps us find what's weird about it. What's weird about it helps us flag what are the ways that we know how to do these things and bust open a ring. What are the ways that we know how to make carbon-carbon bonds. From there, we work backwards and forward, and we take it a step at a time. But thank you for coming to the section supplement. Again, the video will be posted of this, so party groovy. I'll stick around for some questions.